Okay, hello Precalc C, Friday afternoon. I said this video is coming. I'm going to teach you how to compute a 3x3 determinant. Okay, what is a determinant? Good question. We have seen determinants with 2x2 matrices, and the determinant of a 2x2 matrix we discovered initially was the thing which told you whether the matrix was invertible. And if it's 0, the matrix is not invertible, and if it's not 0, it is invertible. We also saw that the determinant of a 2x2 matrix is the thing that shows up in the denominator when you're solving a system of equations. It's the determinant of the coefficient matrix. Okay, so and then there's this sort of geometric interpretation. All right, so 3x3 determinants also have all these same properties. But you might have to kind of just trust me on this a little bit, that if a 3x3 matrix like this one has a determinant of 0, it means that it's not invertible. And when you solve a system of 3 equations in 3 variables, the denominator of the solutions in general will be a 3x3 determinant. And there's a geometric significance to 3x3 determinants, which I'll talk about later. Okay, but right now, I'm just going to teach you how to do this. And okay, this is going to seem like a low intellectual type lesson because I'm just going to tell you how without sort of explaining why. And I'll just say that this is what everybody does. So I'm not the only one doing this. And it's quite difficult to do this kind of better. All right, so enough of that. Let's jump right in. How do I do it? How do I do this determinant? Okay. Well, first I have to introduce a whole bunch of vocab. So there are these things called minors. Okay. What is a minor? Well, the row, and please feel free to watch this on 1.5 or 2 times speed. The row I, column J minor. That's what I'm defining right now. The row I, column J minor, which has a sort of a symbol for it, Mij, is the determinant of the matrix that results from deleting from deleting row I and column J. Row I and column J. Okay. Well, what does that even mean? I can give an example. Here's an example. Take this matrix right here, and suppose I want to compute the M23 minor. Okay, what is the M23 minor? Well, what you're supposed to do is go over here to this 3x3 matrix and go to row 2 and sort of mentally delete row 2. And also mentally delete column 3. That's what 2, 3 means. Row 2, column 3. And when you do that, then 4 numbers are left and kind of smush them back together. And what you get is 2, -1, 1, 6. And you compute that determinant. And okay, we know how to do this. We know how to do 2x2 determinants because we sort of stumbled upon this, or rather, we defined the determinant as 2 times 6 minus 1 times -1, and so whatever, we get just 13 here. Okay, and so actually this sort of, what counts as a minor is recursive. My definition for how to compute a minor of a 3x3 matrix assumes that you already know how to compute 2x2 determinants. So it's in that sense that it's recursive. All right, and now I'm going to introduce another thing called a cofactor. All right, so what's a cofactor? Well, the row I, column J cofactor, which is what I'm defining right now, which I will abbreviate Cij, is a signed minor. Okay, is a signed minor. which is just another way of saying it's a minor, but with a -1 in front of it sometimes. Specifically, there's a formula. The Cij minor is -1 to the I plus j times the Mij minor. Oh man. What does that mean? Well, okay, let's do an example. What is C12? Well, to compute the C12 cofactor, according to this formula, you take -1 to the 1 plus 2. In other words, you just take the row number and the column number, you add them up, and if it's odd, like it is here, then -1 cubed, then it's negative, and if it's even, then it's not. So this is -1 to the 1 plus 2 times the M12 minor. And so in this case, because I'm computing C12, I'm in row 1, column 2, that adds up to 3, that's odd, so it does get a negative, and we put a negative in front of the 1-2 minor. What's the 1-2 minor? Well, it's what you get from deleting row 1 and column 2, leaving you with this 0, -2, 1, 3 type thing. And okay, that I think I can do in my head. It's 0 minus -2, so that determinant is 2, and so my answer is -2. Okay, great. And sort of what that means is you could almost, this is like the real definition, but if all you were caring about was computing 3 by 3 determinants, then you could sort of just get away with memorizing this kind of pattern, which is, when you're in row 1, column 1, that's 1 plus 1 adds up to 2, that's even. So that number in that spot gets a plus in front of it, it doesn't get a negative in front of it. But when you're in row 1, column 2, that's 1 plus 2 is 3, so that's odd, so that does get a negative in front of it. And just in general, if the row and column number 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, and 3, 3, then this little picture I just made is the sort of summary of when the minor gets a negative in front of it and when it doesn't. Okay, so what is the point of all of this crazy and obscure notation? Well, now I'll just kind of do the thing. To compute a 3 by 3 determinant, you expand across any particular row or column. So I'm going to do 2 of these. The first one I'll do is along row 3. And then I'm going to try to squeeze it into this same board. I think I can do that. I will do it along column 2. Okay. So, alright, well let's go. What does it mean to go along row 3? Well, basically, here is the formula for how to do this. You choose a particular row or column. Here I have arbitrarily chosen row 3. And what you do, here I'm giving out the answer to how you do this 3 by 3 determinant. You go to the first entry in row 3, which is this thing. So that's A31. I'm letting A31 be my notation for the entry in row 3, column 1, times the 3, 1 cofactor. In other words, you multiply the number in this spot times the cofactor associated with that spot, plus, and then you just keep doing that along that row. So A32, in other words, the entry in the row 3, column 2, times the cofactor associated with 3, 2, and then plus A33, C33. Alright, what does all that mean? Well, I might not be able to fit this. I think I can. So what is the number in the 3, 1 spot? Well, it's a 1 times, well, what's the 3, 1 cofactor? Well, first of all, cofactor 3, 1, because 3 plus 1 adds up to 4, which is even. It doesn't get a negative in front of it. So I'm just going to now multiply by the determinant of the 2 by 2 matrix that results from deleting this row 3 and column 1. Because that's what C31 is. I delete row 3, column 1, and I'm left with the 2 by 2 matrix, -1, 4, 5, -2. Okay, plus, now what is the number in the A32 spot? It's a 6, times, but now C32, cofactor 3C2, because 3 plus 2 is 5 and 5 is odd, means that I put a -1 in front of the 32 minor, if you're following all this, and that is what you get when you delete row 3 and column 2. When you delete row 3 and column 2, you get this 2, 4, 0, -2 thing. Okay, and now plus A33 is the number in the 3, spot, times the 3, cofactor. 3 plus 3 is 6. That's even, so I don't put a negative in front of it. And I delete the row 3, column 3, leaving me with this 2, -1, 0, 5 thing. Okay, and now I'm just going to crank all this out. I'll just sort of be careful here. So what do I get? I get 1 times, what is this determinant? I'm going to do this in my head because I'm a professional. That's 2 minus 20, so that's -18. Plus, here I have 6 times -1, so that's -6 times, and when I do this determinant, that's -4 minus 0, so it's just -4, and finally, I have 3 times, this determinant is going to be 10 minus 0, so that's 10. So if I did that right, then I get -18 plus 24 plus 30, and I think I did do that right, so I think I get 36. Okay. So, this is like nothing even I don't even know if I would call this math. I'm just sort of explaining to you this algorithm for computing the determinant. Alright, a couple more things to note is that, there's flexibility here, right? Because I can, as I said, there was nothing special about choosing row 3. This method is called expansion by minors. Perhaps it should instead be called expansion by cofactors. It's just, it says you can go along any row or any column you choose. So for example, let's just, instead of doing it along row 3, let's do it along column 2, just to make sure we understand the definition. Well, if we're going to do it along column 2, then you just kind of repeat the same thing, right? It's the thing in the first number in column 2 is A12, the entry in row 1, column 2, times the 1, 2 cofactor, plus the next number in column 2 is A22, and then times C22, plus that number, that's 6, which is just A23, row 3, column 2, so it's A32, C32. Okay, cool. And okay, that's interesting. Hold on, did I mess up? I'm going along column 2. So row 1, column 2, row 2, column 2, row 3, column 2. It's interesting I did that wrong on my paper, or I just wrote the wrong thing. A little typo there. Woo! I guess same brain. Not surprising I made the same mistake, but I think that is just right, because that's row 3, column 2 is the 6. Okay, anyway, now we just do it. So, what is A12? Well, it's -1. But now I'm going to compute the 1, 2 cofactor. Well, 1 plus 2 is 3, that's odd. So I insert another negative in front of the 1, 2 minor. And that's row 1, column 2. Mentally deleting row 1 and column 2 leaves me with 0, -2, 1, 3. Okay, plus, and then A22 is 5, and 2 plus 2 is 4, that's even, so I don't put a -1 in front of the 2, 2 minor. the 2 minors, the matrix that results from deleting row 2 and column 2, leaving me with the 2 by 2 matrix 2, 4, 1, 3, plus what is in that spot is a 6, but 3 plus 2 is 5, which is odd, so I stick a -1 in front of the 3, 2 minor. The 3, 2 minor is the minor that results from deleting row 3 and column 2, leaving me with this 2 by 2 determinant 2, 4, 0, -2. Okay, and now I'll just compute this, sitting on the floor here. -1 and the second one is 1. This determinant is 0 minus -2. So that is actually just +2. Yeah. Plus 5 times, what is this determinant? Well, it's 6 minus 4, so that's 2. And here we get plus -6 times, what do we get here? Is -4 minus 0, so that's -4. So this is 2 plus 10 plus 24, and indeed we got 36. And my claim is that it doesn't matter along what row or column you go, you're always going to get the same thing. So I just redid this problem. I sort of did this problem in 2 different ways just to prove a point that what row or what column you choose is arbitrary. Okay, this was like, you know, not so deep or anything. I probably could have just told you to read the book or let you, you know, find a video online or something to explain this, because I didn't really justify it at all. And I guess I probably won't right now. I'll say a couple more things. So okay. Just erase this. Trying to keep this video sort of short. So. Well, okay. This process actually, the thing I just explained to you was more general than just computing 3 by 3 determinants. In fact, this is really, what I've really just explained is a general method for computing determinants of any size. This method called expansion by minors. And if you want to compute some very, very big determinants, then, well, you just do it. And when you expand by minors, the sort of algorithm instructs you to always like delete a row and a column, and so you're left with a matrix of one size lower. And so this is recursive. Notice how when I computed these 3 by 3 determinants, I needed to already know how to do 2 by 2 determinants. Well, if you know how to do 3 by 3 determinants, and we do know now, you can compute 4 by 4 determinants. So I will now give you one 4 by 4 determinant to be done by hand. I will never ask you to do this. I think ever again. I don't know. Maybe one homework problem. But just trying to kind of prove a point. If this is your last time, this is the only time in your whole life that you learn about determinants, I'd like you to at least see that that this is more general than what I just explained. So okay, here we go. Here, or maybe I'll go onto a new line or something. So this is a 4 by 4 determinant. How am I going to do this? Well, I said we can go along any row or column. So one, I think, very smart thing to do is to look out for a row or column with a lot of zeros in it, because that's just kind of nice. So this column right here, 2004, just like it has 2 zeros. So that means like less work, right? So all right, if you understood this whole process, what am I supposed to do? I'm supposed to put, I'm choosing now to expand along column 2. So if I expand along column 2, I get 2 times, well, this is row 1, column 2, that adds up to 3, that's odd, so I get a negative, times the determinant of the matrix which results from deleting row 1, column 2. And so this should be cha-cha-cha. Some powers of visualization required here. Yeah, well, that's looks right. Okay. Well, now what's sort of next? Well, next is 0 times. Well, this is row 2, column 2. So, but okay, this is kind of just a little bit silly, right? I'm going to write what's in here. It's the matrix which results from deleting row 2, column 2. But of course, I don't have to actually compute it because the 0. So that's nice. I get sort of 1 for free. And then the very next number is also a 0. So, but this is row 3, column 2, which is 5. So you're supposed to throw a -1 in front of the matrix, which results from deleting row 3 in column 2. So once again, just being sort of careful here. And 0, 1, 6. I get that matrix, but I don't really have to do it. And then finally, I get this 4, which is row 2, column 4, so that adds up to 6, that's even. So I don't put a negative in front of that minor. And now I write down the matrix, the 3x3 matrix that results from deleting row 4, column 2, and it's this one. Okay. Okay, so I don't love this because man, I have to do so much work still, right? This is the sense in which it's recursive. To compute this 4x4 determinant, I have to compute all of these 3x3 determinants. Now, I don't actually have to do this one because it's 0, but in general, if none of the numbers is 0, then to compute a 4x4 determinant, you have to compute 4 3x3 determinants. And if you want to do a 5x5 determinant, then you're going to have to do 5 4x4 determinants. Okay, so if you know something about this, if you're taking computer science right now and you want to analyze this algorithm for its sort of efficiency, you would say that this is like big O of like n factorial, which is to say that as the size of the matrix, I think I'm saying that right, as the size of the matrix increases, if you give me a 7x7 determinant to compute, it's going to take me, I have to do 7 6x6 determinants. Each of those is going to take, 6 5x5s. And so, in fact, you're sort of doing a 7 factorial amount of work or something like that. So the length of time that it takes to compute this is growing factorially. Okay, so that's bad. All right, well, fortunately we have computers, and also we're not really going to do much with 4D in this class, or hardly anything. All right, I'll say one last thing, which is that this really is recursive in the sense that, it's so far you've seen it's recursive in that we've sort of discovered the 2x2 determinant, and now I've defined how to compute the 3x3 determinant in terms of the 2x2 determinants. But if you wanted to go all the way, you could define the determinant of a 1x1 matrix to just be, the number. And if you define the determinant of a 1x1 matrix to just be, that number, then I can actually compute a 2x2 determinant according to this formula, according to this recursive rule. Okay, so let's just do it. If I've fully digested this algorithm for expansion by minors, then I can expand this by minors. So I guess I will just choose row 1 because why not? And okay, what am I supposed to do? I'm supposed to write the if I'm going along row 1, I take the first thing in row 1, which is A, times the 1, 1 cofactor. Perhaps it's worth, I don't think we need to write it. So what is the 1, 1 cofactor? Well, this is row 1, column 1, so that adds up to 2, so I don't put a negative in front of it. I mentally delete row 1 and column 1, leaving me with a 1x1 matrix D, and I'm supposed to be multiplying, taking the determinant of that. Okay, plus, now I go to the next thing in row 1, which is that B. But then, because I'm in row 1, column 2 now, 1 plus 2 adds up to 3, that's odd. So I stick a -1 in front of the determinant of the matrix that results from deleting row 1, column 2, which is just C. Okay, but of course, the determinant of this 1 by 1 I just gave you right now in this base case is just that number, and so we get AD minus BC. Okay, in other words, if you want to, and this is what fancy people do, like if you were to Google, if you were to type determinant into Wikipedia or something, what I think you will find, it's been a while since I've checked, but once upon a time at least, what you would find is a what you would find is a definition of the determinant. The definition that they would give of determinant is actually this recursive definition. In a somewhat kind of unsatisfying way, they would just, if you just sort of ask Wikipedia, hey, what's a determinant? Instead of giving you the sort of deep understanding of it all, or the story, or the geometric interpretation, or the meaning, they would just be like, okay, base case. The determinant of a 1 by 1 matrix is just that number. For all higher dimensions, then the determinant is defined via this process called expansion by minors. And then, if you do it that way, which is not how we're going to pursue it in this class, then you would have to sort of show that this artificial sort of object that you've defined actually has all these interesting properties that you want to say it has, such as being significant for the inverse of a matrix. Okay, I think in period 3 and 4 we finished nicely, so I think you can stop watching right now. For period 6, if you could just watch for 2 more minutes, because what we were doing at the very end of class today was talking about this thing called Kramers Rule, and the one thing I didn't get to was mentioning Kramers Rule in for 3 by 3 for a system of 3 equations and 3 variables. So let me just do that really fast. If you have ax plus by plus cz, and then it's typical to sort of go like this. So d, e, f, g, h, I, and then let these be j, k, l. So suppose I wanted to solve this system of equations like in general. This is something that you could do. It's quite tedious. And if you do this, if you work this all out, by hand or something with Gaussian elimination, it would be terrible. And what you're going to get is some, sort of giant, disgusting formula, assuming that this system of equations has one solution, one unique solution, so that the 3 planes meet at a point. If so, you'll get a formula. What's that formula going to look like? Well, Kramers Rule applies in the 3D case as well. And so, if you want to know what the solution for the x variable is, for example, well, our friend, the determinant also makes an appearance here. And so, once again, the determinant of the, just like for the 2 by 2 case, the determinant of the coefficient matrix sort of shows up in the denominator of the general solution. And this will happen for y too. For y also, you'll get a, b, c, d, e, f, g, h, i. Okay. So that's one thing that I'm not going to prove that that's true, but that is true. And how do you sort of remember what the numerator should be? Well, Kramers Rule, as we talked about it in class for the 2 by 2 case, says if you want to know what the coefficient, what the numerator of the coefficient, if you want to know what the numerator of the general solution for x is, then you replace the x coefficients with the constants. And that gives you this 3 by 3 matrix, J, K, L, B, E, H, and C, F, I. Okay, and that is actually the solution in general, x. And for y, you replace J, K, and L in for B, E, H. And you take the determinant of that, you get the numerator. Okay, so that's sort of the usefulness of maybe 3 by 3 determinants, although you're just trusting me on that. And of course, if the determinant of this coefficient matrix is 0, yeah, well then the system either has no solutions or an infinite number of solutions. So the formula doesn't work. Okay, goodbye.